Assalamu alaikum class. In this video we are going to discuss about some formulas relating to the del operator. Previously we have started chapter number 4 in which we discussed about the del operator, which is basically a differential operator, and we discussed three different operations like divergence, curl and gradient using this one differential operator which is named as the del operator. Now the first one is that del of phi plus psi is equal to del of phi plus del of psi. Here psi and phi both are the two scalar functions, or you can see that the gradient of phi plus psi is equal to gradient of phi plus gradient of psi. Then we have divergence, that del dot a plus b is equal to del dot a plus del dot b. Similarly, it is defined for the curl as well, that either you are going to apply on the resultant or you may apply on the single vectors, and then you can find out the resultant of the vectors. Next we have fourth one, that del dot phi a. Here phi is a scalar term and a is a vector quantity. So here you can see that this dot operator or the dot product is going to be defined as, this is going to be del of phi dot a plus phi del dot a. This could be realized, or this could be mentioned with the help of the product rule, as we discussed about in the derivatives, that when we have to find out the derivative of a product term, we apply the derivative of first term into the second plus derivative of second term into the first one. So here you can also see that the del operator is a differential operator or involves the derivative. So for the product term we have the derivative of one function second as it is, then derivative of the other function, and the other second function will remain the same. So next we have the fifth one, del cross phi a. Here we are going to define about the curl, that del cross phi of a, del cross phi of a. Here phi is a scalar term and a is a vector quantity, so again del of phi cross a plus phi into del cross a. So next we have del dot a cross b. Here now we have the divergence of the cross product, that how we are going to deal with this, b dot del cross a minus a dot del cross b. Now in this rule or in this formula, the position is really very important, because we are having a sign of negative over here, because if I change the position, obviously the answer is going to change its sign. So the positions of the terms are very important, at b dot del cross a, then a dot del cross b. Next we have the curl of the cross product of the two vectors, del cross a cross b. So this is going to be b dot del into a minus b dot into del dot a minus a dot del into b plus a into del dot b. So this is the formula for del cross a cross b. Here we have the formula for del of a dot b. Clearly it is going to define the gradient, because a dot b is a scalar term, and del of a scalar term is defined as the gradient of some term. Next we have the fifth rule, which is about del dot del of phi, that is the double operator or the square operator. This is also named as a Laplacian operator. Del cross of phi, in del cross is obviously, or del square is obviously defined the double derivative. So del square is going to define over here del dot del of phi, that is del square phi, and this is going to define the second order derivatives in it. This is also named as a Laplacian operator. Next we have del cross del of phi. It is going to be zero vector. The curl of the gradient is always 0, and the divergence of the curl is also a 0 term, or is also a 0 scalar. Next we have del cross a. This is going to be del of del dot a minus del square a. So this is how we define different formulas related to the del operator. Next we are going to solve some questions related to the formulas we have recently discussed, that a vector v is called irrotational if curl of v is equal to 0. So this is how we are going to define a new term, that irrotational, how we named a vector to be rotational. If the curl of that vector is 0, that is del cross v will be 0 vector, then we will name that vector to be an irrotational vector, because the curl also named as a rotation. So find constant a, b and c so that the given vector v is irrotational. Irrotational means its cross product or the del cross v must be 0. So here we have defined the del cross v. Del is obviously partial by partial x, partial by partial y and partial by partial z, and here are the components of v, and here we have defined the del cross v or the curl product or the curl of the vector v. Now we are saying that for being irrotational, its curl must be 0, 0 vector, that is each component must be 0. So we will put c plus 1 0, a minus 4 0 and b minus 2 is equal to 0. So we get the values of a, b and c in this case, that is here we have defined the vector v. Now in the second part, we have to show that v can be expressed as a gradient of a scalar function. So it means that we are going to assume that v is equal to gradient of some scalar function, and scalar is assumed to be phi over here, that is v is equal to del of phi. So del of phi will be clearly partial phi by partial x, partial phi by partial y and partial phi by partial z. Now v is a vector quantity and this one is a vector quantity, and we know that the two vectors will be equal if they have the same components, if they have the equal components. So we are going to simply replace it that the I component of this vector must be equal to the I component of vector v, similarly the y component and similarly the z component. So x component, y component and z components are we are going to relate, or we are going to equate the corresponding components, and we will get the three equations. Now we are going to partially integrate these equations one by one, and we will get a function which is going to be defined as phi. So by integrating it with respect to x, we get phi is equal to x square by 2 plus 2xy plus 4xz plus some function of y and z, because when we talk about the partial derivatives of a triple variable function or the three variable functions, then and we are taking the derivative with respect to x, then we will treat y and z as a constant function. So when we are going to deal with the partial integrations, we have to put some function of the other variables, not a constant of integration, because when we are going to deal it with respect to x, y and z are treating as a constant terms. Similarly, we will integrate equation 2 with respect to y and in equation 3 with respect to z. So when I am going to integrate this expression with respect to y, I am going to have some function of x and z, and when I am going to integrate this expression with respect to z, I will have some function of x and y. So here we have the function phi when we are dealing with the or integrating equation 2 and 3 respectively, and here we get the common value of phi in this case by simply equating the three definitions or the three values of phi. We get phi, f, g and h, and we can define one single function phi over here. So here we are having a generalized rule that whenever the curl of some vector function is 0, that is del cross v is equal to 0, we are able to find out a scalar function phi such that v is equal to del of phi or the gradient of phi. And in this case, when v is equal to del of phi or the gradient of the scalar function phi, the vector is named as the conservative vector, and the scalar function phi is named as a scalar potential. Here we have question number 46, in which we have to prove that del of f of some function r is equal to f prime of r into vector r over r. Here r is representing the magnitude of the vector, and here is a vector quantity, and f is a function of the magnitude of r, which is basically a vector function, vector quantity, this one, and this is a scalar quantity. Now r is equal to xi cap plus yj cap plus zk cap. Clearly r is representing its magnitude, so it will be equal to square root of x square plus y square plus z square. Now we are going to define del of f of r, that is the del operator is going to apply on this function f or the scalar function f. It is going to be partial f by partial x, partial f by partial y j cap plus partial f by partial z k cap. Now clearly when I am going to deal with partial f by partial x, so f is depending on r, so I am able to apply the chain rule over here, that is partial f by partial r into partial r r by partial x. So this is going to be f prime of r, and we can apply the derivative on this term because r is equal to square root of x square plus y square plus z square. So applying the power rule over here, 1 by 2 x square plus y square plus z square whole power minus 1 by 2, and then we will take the derivative of the base, which is going to be 2x. So this 2 and 2 will be cancelled out, and I am going to have x into x square plus y square plus z square whole power minus 1 by 2 into f of prime of r. Clearly we can also find out partial f by partial x, in which we will have y over here and all the terms will be the same. So inserting the values, we get f prime of r into x square plus y square plus z square whole power minus 1 by 2 into xi cap plus yj cap plus zk cap. So this is going to be defined the quantity r, or 1 over r. So here we have the final result that we have to prove. Next we have question number 47. We have to evaluate del of 3r square minus 4 square root of r plus 6 by 3 square root of r. So clearly we can apply the previous result over here, in which we simply need to take the derivative of the function f. So f of r is equal to 3r square minus 4 square root of r plus 6 by 3 into square root of r. So sorry, it's cube root of r. So simply taking the derivative over here, we get the result on, and then we can insert the values over here in the formula. So here is the derivative 3r square. The derivative of 3r square is 6 into r. The derivative of this term will be minus 4 as it is, and we will apply the power rule on r power 1 by 2. So 1 by 2 into r raised to the power minus 1 by 2. 6 as it is, this is cube root of r, that is r raised to the power minus 1 by 3, because that term was in the denominator. So applying the power rule, minus 1 by 3 r raised to the power minus 4 by 3, and by inserting the value we get the result over here. Next we have question number 60. Find an equation for the tangent plane to the surface at the point 1, minus 3 and 2. Now at first we will find out the normal to the surface, which is obviously the gradient of the surface, or the gradient of the function phi, and phi is defined to be this function. So gradient of phi is going to be a del of phi, which is defined to be this term. And now obviously the gradient of phi is defined to be the normal to the surface, so we may name it is to be n. So n, the unit normal, is defined to be minus 2i cap plus j cap plus 3k cap. Clearly we have insert the values of x, y and z of the given point over here. Now clearly equation of a plane passing through a point with position vector r naught and perpendicular to the normal n is defined to be r minus r naught dot n is equal to 0, as we have discussed previously. So simply inserting the values over here, r vector is x, y, z, and r naught, the vector defined over here, 1, minus 3 and 2 the components, and n is defined to be the gradient of y. So inserting the values over here, we can get the equation of the required tangent plane, and here is the final equation for that. Next we have question number 84, in which we have to show that the given vector is solenoidal. Any vector A is said to be solenoidal if its divergence is 0, that is del dot A is equal to 0. So del dot A is simply a partial by partial x of x component, partial by partial y of y component, and then partial by partial z of z component, which is 0 in this case. Hence the given vector is solenoidal.